My name is Harrison Leary, and this is my Physics 2211 Lab 4. So for this lab, the purpose is to analyze the properties of the energy principle through oscillating motion created by using the tracker software on the provided video. So there are a variety of physics principles used here. The most basic one is that the total energy is equal to the sum of the kinetic energy, spring potential energy, and gravitational potential energy. And I have the formulas for all of those energies listed below. So the kinetic energy simplifies to 1/2 mv squared, the spring potential energy simplifies to 1/2 kx squared, and the gravitational potential energy simplifies to mgh. Then the forces, the spring force simplifies to k times the change in distance times L hat, and the gravitational force simplifies to mg. Then finally, some basic formulas. The period is equal to 2 pi times the root of the mass over the spring constant, and then the velocity update and position update formulas are below. So for the experiment, I'll play this while I list my initial conditions. So the mass of the object is 0.402 kilograms, and my initial position was found to be negative 0.107 x and negative 0.6611 y. And the length of the string was said to be 0.7 meters. Our initial velocity was 0, and the spring constant was calculated to be 6.87 newtons per meter using the period formula I discussed earlier. So for the coding, the result of inputting those positions found in the video into the code is this here, after also replacing all the formulas in the code. So the red dot on the video is the ones from the tracker software, and the blue one is the calculated one using the code on the glow script. So then on the various graphs here, on the one on the right, we have the change in energy versus time, where you can see the transfer of energy through the energy principle, where as the position is changing, the potential energy is shifting between the gravitational potential energy and the spring potential energy, while also the motion is causing changes in the kinetic energy. But the sum of all these energies at any given time is equal to the delta E, the total energy, which is always 0, as all these energies cancel out. And then on the x position versus time and y position versus time graphs, you can see that there is a slight discrepancy between the two graphs, but ultimately they are mostly the same, as the forces are mostly accounted for, but there are some discrepancies, such as no accounting for drag force or friction or anything like that. So then for the code that I did change, I updated the initial values, such as the mass of the object, its position, its initial velocity, and so on, along with the spring constant and the relaxed length of the spring. Then for the formulas, I put the formulas that we discussed earlier in the physics principle section into the code. So that would be all these formulas on the bottom left for L, L hat, and S. Those are all what were found before, along with all those energies. And then using those formulas, we're able to update the change for the motion of the object, and that will update the energy, update the graphs, and so on. All right, so for the conclusion, is the energy principle satisfied? So yes, the energy principle is satisfied. That's what was shown on the energy graph I showed earlier, where the delta E is consistently 0 because all of the different energies cancel out. Then find the two periods of oscillation from the x position and the y position data. So we got two different values. For x, I estimated 1.646 seconds, and for y, 1.519 seconds. So the reason these would be a little different is that the spring constant is not exact in both directions, and there would be some variation, which would cause a bit of a discrepancy in the periods. And that's all.